This is again Chapter 9 of Munson's book. In the part explaining the Reynolds number dependence of the drag coefficient, creeping flows are mentioned, which are flows with Reynolds number less than 1. Reynolds number can be small if the fluid speed is low, body size is small, fluid viscosity is high, or density is low. In these flows the drag coefficient is inversely proportional with the Reynolds number. Drag coefficients of some objects under creeping flow condition are given in this table. For a sphere the drag coefficient is 24 over Reynolds number, which is known as the Stokes equation. Although creeping flows seem to be extreme cases due to their very low Reynolds numbers, it is possible to find them in everyday life, such as an influenza pandemic we are facing nowadays. Viruses, such as coronaviruses, are known to be transmitted from person to person through cough droplets. So, how large are these droplets and at what speed do they move in air? According to this research study, a typical cough droplet is less than a 1 micrometer in size. And the speed of the droplets? According to this website of American Lung Association, a cough can travel as fast as 50 miles per hour, which is about 20 meters per second. Now we can calculate the Reynolds number of a typical cough droplet. A droplet of diameter 0.3 micrometer, moving at a speed of 20 meters per second in standard air, with properties shown, will give us a Reynolds number of about 0.4, which makes this flow a creeping flow. It is important to know the drag force acting by air on the cough droplets to estimate their trajectories correctly. How far do they move and how long does it take for them fall to the ground? In applications such as this one and many others, creeping flows are encountered. Although we've talked about cough droplets, we are not going to simulate flow over a sphere in this tutorial. Rather we will consider a two-dimensional circular object, which is more of a model for a cylinder rather than a sphere. A sphere can also be used, but such a simulation needs to be three-dimensional, and we prefer a 2D one here, due to its simplicity. So, it is better to call it flow over a 2D cylinder. Remember how similar the drag coefficient versus Reynolds number curves of cylinders and spheres are. For a cylinder at Reynolds number 0.4, the drag coefficient is about 20. This is the value we will try to get in our simulation. The most important non-dimensional parameter in our simulation is the Reynolds number, which we will take as 0.4. The density and viscosity of air at standard conditions are known. We can pick a diameter value and calculate the corresponding free stream speed, u, to get the desired Reynolds number. The diameter and the free stream speed need not be the same as the ones of the actual problem. For example, to study a cough droplet we do not need to use a micrometer-sized object. We can pick any speed and diameter combination, as long as the Reynolds number is the one we want. Therefore, we can pick an easy-to-work-with diameter, such as 1 mm, and calculate the corresponding speed to get the Reynolds number of 0.4. This calculation will result in a speed of 6 mm per second. Therefore, these two problems, with different speed and diameter combinations, provide the same Reynolds number of 0.4. The one on the left is more like the cough droplet problem, but we are going to simulate the one on the right, because in engineering software, it is easier to work with millimeter-sized objects rather than micrometer-sized ones. To simulate the external flow over an object, we need to place it inside an artificial box, similar to putting it inside the test section of a wind tunnel when we do an experiment. Just like in the wind tunnel experiment, we will consider the object to be fixed and the air is blowing over it. The artificial box needs to be large enough such that the boundary conditions we define on it will not affect the flow over the actual object considerably. The blue region shown inside the box and outside the circle is filled with air, and it is the problem domain. Parameters of the problem that will be used during the simulation are as shown. As seen, the artificial box is taken to be 80 times larger than the circular object, which is a value selected based on experience of solving similar problems previously. When we simulate a problem with CFD, we use numerical techniques to solve partial differential equations inside the problem domain. And to do that we need to define conditions at its boundaries. Boundary conditions that we are going to use are as shown. At the inlet we provide a uniform known speed. At the exit, typically a constant gauge pressure is specified for incompressible flows, such as this one. The circular object itself has no slip condition on it. And the top and bottom edges of the artificial box are defined to be slip walls with zero shear stress, so that their effect on the flow is minimized.